Hello, everybody. My name is Max Cembalest. I'm here with my colleague Rowan Cheung from Arthur. We are a machine learning monitoring and performance startup based in New York, and we're here to talk about LLM guided evaluation. So, as an outline of our talk, we're going to give a bit of the background of why we're focusing on LLM guided evaluation. It's a product we're working on called Arthur Bench. We're going to go through a brief history of evaluating text in the world before LLMs. We're going to give a brief overview of how LLMs have been used so far to guide the evaluation of text. And then we're going to show you some experiments that we have been doing that are meant to address the questions of how should this LLM guided evaluation be done? And can this kind of LLM guided evaluation be actionable in a production setting? So a bit of background on what we're working on. We are two machine learning engineers at Arthur working on a product called Bench, which is an open source library for benchmarking the performance of different LLMs, different prompts, different generation settings like temperature, all meant to compare how the generative text looks on your custom data that you're trying to work with in production. So some common generative text tasks that we've been focusing on supporting so far are summarization, question answering, and in addition to some more classical and time-tested scoring methods for those tasks, we've included out of the box with Arthur Bench some prompts to use GPT 3.5 Turbo to evaluate summaries or to evaluate answers to questions. And, we've seen this emerging as a kind of common, quick way that data scientists are starting to evaluate their summary models or evaluate their question answering models. You prompt GPT 3.5 Turbo to give feedback on the summaries or to give feedback on the answers. So the general question we're trying to address today is, what is this like to use LLMs to evaluate other LLMs? When does it make sense to do this? To get a bit more concrete on what we mean by evaluation, we're just referring to whatever tests and metrics are being used to judge a generative text model for production readiness. So on the right side of the screen here, I have an example news article from August 2023, and we have an attempt at summarizing this article at the bottom. So to evaluate the quality of a summary should be somewhere between the most strict and concrete possible evaluation, which is the text of the summary exactly the text that one expected, or the least strict and concrete way to evaluate the summary, which is, does the summary have the right vibe? Really, text evaluation should be somewhere in between these extremes. You should be able to handle flexibly a large space of possibly correct or approximately correct summaries. So that is what we're going to cover. What does it look like to evaluate otherwise subjective tasks like summarization? We're going to cover what this looked like before LLMs came onto the scene, and then we're going to discuss what it looks like to use LLMs to do this kind of evaluation.
So I'll cover a few commonly used techniques for evaluating generated text that don't involve prompting any language models. We generally think about these in a few different categories. The first is measuring word presence. So this could be something like the overlap between words in an output compared to a reference text, or it could be something as simple as just the length of the sequence, how many words occurred. The next category actually leverages pre-trained NLP models. So this could be either extracting embeddings from these models to then use in a similarity score, or actually fine-tuning these models for a evaluation task. This could be something like classification or entailment class, or faithfulness. And the third class, which we won't cover in depth in this talk, is running perturbation tests. So essentially, these tweak or switch perturb words in the input to the language model and see what changes in the output generated. These are really commonly used for both fairness and robustness testing. So to get a sense of some of the pros and cons of using the first two categories, I'm going to walk through an example. So we have 3 sentences here. And as you can see, all 3 of these sentences have to do with the speaker being cold. It is cold outside, and the speaker wants to remain inside of their car. However, in sentence 1 and sentence 2, we see large, completely overlapping spans of text. Whereas in sentence 3, you're seeing a lot of synonyms for words in sentence 1 and sentence 2, but not a lot of actual overlapping spans. So we're subbing in frigid for cold, vehicle for car, etc. So looking how kind of a very common metric in this category, the BLUE score, compares that rating these 2 sentences. Essentially what BLUE is looking for at a very high level is how many words in the candidate model generated output also occur in the reference words or n-grams. And looking at the BLUE score when we hold sentence 1 as a reference and compare sentence 2, we see this has a very high score because we do have that full overlapping span of I could barely spend more than 10 minutes outside. But then when we instead evaluate sentence 3 compared to a reference of sentence 1, we see the BLUE score drop considerably. And this is because BLUE score is not able to pick up the semantic meaning of sentence 3 and realize that it is very similar to sentence 1. So moving to the next class of using a pre-trained NLP model, we are looking at BERT score, which seeks to do a similar type of measurement of the kind of like overlapping tokens between each of these sentences, but instead of using the raw tokens themselves, we are using contextual embeddings drawn from a pre-trained LLM like BERT or any other, and repeating the same measurements of evaluating sentence 2 to a reference of sentence 1 and sentence 3 to a reference of sentence 1, we see that the BERT score is much more consistent across these 2 evaluations. So we're able to successfully use the embeddings and the pre-trained knowledge to get a score that takes into the semantic meaning of these sentences.
So in contrast to the kind of evaluation that we've been showing so far, LLMs as evaluators follow the following basic process. You have model-generated text, which you format into a prompt template, which is sent to some LLM that provides feedback. So this is a very general procedure that you can adapt to use LLMs to give feedback the same way that you may have used the previous evaluation methods that we've been discussing to provide feedback on machine translation or to provide feedback on how close a summary hews to its original article. So what does this actually look like in practice? The most common way that the LLMs are being used to provide feedback is for classification, like classify this response as some number between 1 through 10, where 1 would represent a garbage answer and 10 would represent a perfect answer, or classifying responses as either containing hate speech or not, or classifying responses as containing attempts at disinformation or not. A few well-chosen examples in your prompt template, which you send to a language model, can go a really long way. So this is already a very popular generative text evaluation procedure. You have some custom property that you can describe in a few examples, and then by prompting an LLM with those examples, it can classify more generative text according to those examples. So this is what we generally follow for our summarization evaluation and for our question answering evaluation. We have GPT 3.5 Turbo act as a classifier for the generated text using few-shot prompting. And this is working, decently well so far, especially relative to how little time it takes to actually set up. Another general way that LLM guided evaluation is working, instead of classification, is taking the unstructured text that's produced and converting it into structured data. So this could look like parsing custom metadata from text that's generated, or taking text and converting it into a structured knowledge graph representation of that text. This is a general direction that we think has a lot of promise, but is still relatively in its infancy. And we don't cover it in our talk. We just focus in this talk on LLM guided evaluation for classifying responses. So when would this help? The basic way that we see this is that it helps in your iteration and experimentation speed. So it takes very little time to describe in words your evaluation criteria. And it also takes relatively little time to create just a few examples of your evaluation criteria. For example, evaluating, does this response contain hate speech? This is something that people are building few-shot prompts with, a few dozen examples, and this can act as a first baseline LLM guided classifier to do detection of generated text going forward. The fact that you're describing your evaluation criteria in words and with a small number of examples makes it very quick to iterate on this, slightly changing up the language of the words in your evaluation criteria description, slightly changing up the few examples in your few-shot prompt. By using LLM guided evaluation, you can iterate very quickly on this relative to the iteration speed of iterating on pre-trained NLP models, where you would have to iterate on many more examples and possibly iterate on, much slower training times for pre-training those models. So that's one general benefit, is that LLM guided evaluation is quick to implement. Another benefit is that it is more sensitive in some crucial ways relative to pre-trained NLP models or word presence evaluation methods. So like a great example of this is when just the word not included in a response very much changes up its meaning or its interpretation. And LLM guided evaluation using prompting for classifying responses can be pretty good at flexibly responding to the word not, changing up the meaning of that generated text. We've seen it be better at handling that kind of presence than the pre-trained NLP way of evaluating text. But this extra sensitivity that LLM guided evaluation presents can also make LLM guided evaluation unpredictable and variable. So there's two basic challenges that we want to highlight here. LLMs as evaluators are very sensitive and very variable depending on all the different ways you could set up LLM guided evaluation. So the experiments that we're going to discuss in a bit really touch on that variability. Another difficulty that we want to mention is that LLMs as evaluators of other attempts at generative text are constrained by the difficulty of the task at hand. So if it would require too many reasoning steps or too many variables to be managed simultaneously, LLMs on their own will really struggle with this. A disclaimer is that this will improve over time as people build out more solutions that integrate LLMs with other tools and APIs. And we don't really cover this difficulty constraint in our experiments, but we do want to highlight some research that does just demonstrate very effectively what this constraint looks like. There's a team from the Allen Institute that tried to push transformers to their limits at doing a set of multi-step problems, one of which was just multiplying numbers with a bunch of digits. And even fine-tuning a pretty large language model like GPT-3 on many examples of this kind of multiplication, which requires multiple steps, carry the one, things like that. Once you show it problems that are just slightly bigger than its training examples, even though they're the same basic kind of problem, you get massive correctness drop-offs. This just demonstrates that LLMs will, even when fine-tuned, really, really struggle with multi-step problems, multi-step reasoning problems. And in contrast, a pocket calculator does not exhibit this kind of drop-off in performance when you go from multiplying small numbers to big numbers. So that's a really important constraint to keep in mind if you're considering using LLMs to evaluate in a context that would require many, many steps of reasoning. It's likely to really struggle even when fine-tuned. That's not the focus of our experiments. Our experiments are going to focus on the sensitivity challenge. And we have our basic takeaways here. LLM guided evaluation is very sensitive to which LLM you're choosing to evaluate generative text. What is the task that's being evaluated, and what type of feedback are you prompting for? So this is a quick overview of the first set of experiments we ran. We were taking the kind of two very popular use cases that we've been seeing a lot so far: summarization and question answering some kind of question given some context that can help produce the answer. And we compared 5 different LLMs as candidates on these tasks: GPT 3.5 Turbo, GPT 4, Claude 2 from Anthropic, Llama 2 with 7 billion parameters, and the command model from Cohere. For each of the inputs from each task, we provide that input to the LLM as the candidate to produce output text. And then we provide that set of inputs and outputs to those same LLMs as evaluators, except for GPT-4, due to cost reasons. It would be too expensive for us to have used. And we prompt them for 2 different types of feedback. One round, we prompt them for integer feedback, scoring responses 1 to 10. And another round, we prompt them for letter grade feedback. Our hypothesis going into this experiment was that LLMs would be biased towards the text that they themselves generated as candidates. But this hypothesis was not supported by our findings. Across the board, GPT 3.5 Turbo was the most popular candidate on summarization when being prompted for integer feedback, and on question answering, no matter what kind of feedback. Variety of models was the most popular for the summarization task when getting letter grade feedback. But this just shows that, from these 4 evaluators, there was some rough consensus that GPT 3.5 Turbo produced the highest quality text according to this kind of feedback scheme. But to show a bit more of some of the quantitative and qualitative differences between these models and evaluators, we want to show what the experiment data looks like zoomed in a little bit further. So this slide shows every single inference that we used GPT 3.5 Turbo to evaluate. So each row in these grids corresponds to a single input for an inference, and then each column corresponds to a different candidate attempt at that task. For example, asking Claude to summarize an article, or asking Llama 2 to answer a question given some context. And we can observe here some patterns. One pattern is that on the top, which represents the feedback for summarization, we see lower scores across the board than on the bottom, which shows feedback for question answering. So this just shows that the distribution of feedback that you can expect is going to be different based on the task that you're evaluating. One thing that we wanted to take a look at is to highlight some of the inferences that GPT 3.5 gave very low scores to. Across the board, most of its letter grade scores were in the A to B range. And so as a quick sanity check, here's one of the inferences that got a D grade. So this is an excerpt of text from a climate change report. The question that we threw at these models as candidates is, given this context, answer the question of why be concerned about a change in just a few degrees in average global temperature. We can see that the response in blue, which got an A+ grade from GPT 3.5, sort of answers the question using the information in the context, whereas the answer shown in red, which got a D grade, is actually an exact copy of a part of the text from the excerpt. And it even includes the section heading B.1.4, which I personally agree is a sign of a lower quality answer. A real answer should use the context to generate new text instead of just repeat text with some of these, unnecessary artifacts like section numbers. So this is a quick sanity check that GPT 3.5 Turbo does seem to be giving low grades when those responses deserve it. Now here's Claude 2 as evaluator, which we can compare to GPT 3.5. So relative to GPT 3.5, it gives many more perfect scores to summarization and many fewer perfect scores to question answering. This just highlights that the distribution of feedback that you can expect is not just sensitive to the task that you're evaluating, but also very sensitive to which LLM you're prompting for feedback. We can see some consensus here on the lowest scoring candidates in question answering from Claude 2. Those two boxes highlighted in orange got a B grade, which is on the very low end for Claude. And those are the same two boxes that GPT 3.5 gave a D grade. So this just serves to show that there is some consensus on what the lowest scoring answers are, but GPT 3.5 gives its lowest scores as Ds, whereas Claude gives its lowest scores as Bs. So that just is meant to demonstrate that you can expect very different distributions based on all of these selection choices when you're setting up LLMs to evaluate text. Now, Llama 2 as evaluator, relative to the previous two evaluators that we've covered, is much more uniform in the feedback that it provides. We are seeing across a single input, it will very often give the same grade no matter what all the outputs were. This is way more consistent than the previous two evaluators. We can see in the integer feedback, it is much more fixed to the values 3, 5, and 8, whereas we were seeing a much wider spread of possible feedback scores from the previous two evaluators. So again, sensitivity to the LLM giving the feedback is really high. And now the command model as the evaluator, relative to the previous three evaluators that we've shown, one thing that we observed is that it gives lower scores, like a 5 out of 10, much more frequently than the previous three evaluators. And we see some scores showing up with a -1 in the bottom left, which indicates that there was actually no parsable integer feedback being provided there. This is an example of what I'm talking about. This is the kind of prompt template that we were using to get integer feedback from these evaluators. We have some rubric about what counts as, a 10, what counts as a 1. And then we have the candidate answer. And what we're looking for in the evaluation is any kind of number to extract from there. And plenty of times the command model was not actually able to return a number. This just highlights the importance of using models that have been sufficiently instruction tuned, right? The capacity to follow the instruction is super important for these things to actually serve as evaluators so that they can give the type of feedback that you can parse an action on going forward. I'm going to hand it back now to Rowan.
So we've seen some of the challenges in developing LLMs to be used as evaluators. We wanted to take a step back and say how effective can these be, specifically for the use case of human-in-the-loop validation, and how usable are they compared to some of the previous evaluation methods that we covered in the background. So let's say you are developing a summarization model and you kind of reach the stage where you're manually reading some of those summarizations, trying to gut check how well it's performing and specifically find any failure modes in your model. You're going to be most concerned with trying to get a score or evaluation metric that can surface the kind of lowest performing summarizations aligned with how you would judge those summarizations. Helm was a benchmark released by Stanford recently where they evaluate many LLMs on many scenarios, including summarization. And as part of the release of the benchmark, they also released a data set of human ratings on some of the common summarization benchmarks, such as XSum and CNN Daily Mail. So they asked humans to rate model-generated summaries on faithfulness, coherence, and relevance. And importantly, they also find that some of the automated summarization metrics that they were using for the benchmark, such as Rouge, which is fairly similar to the blue score that we covered, are actually anti-correlated with the results of the human ratings. So we wanted to answer, how does prompting an LLM for feedback compare to using these automated metrics? And we kind of took the simplest possible route to get started with measuring that. And it's just a zero-shot reference-free prompt where we say you are evaluating the quality of a summary. Is the summary faithful, coherent, and relevant? Only respond with yes or no, nothing else. So on the next slide, we have the results on a subset of the XSum annotations from Stanford. And we see GPT 3.5, which we used as the evaluator, showing some slight correlation with the human ratings, not a negative correlation, with the coherence scores having the strongest correlation. So we think this is kind of like a promising measure of using an LLM evaluator to guide your human-in-the-loop validation, and are excited about next steps that could take the faithfulness and relevance scores even further, such as different type of feedback scores, like Max said, using letter grades or probabilities moving forward. Yes. In conclusion, we can't recommend any one-size-fits-all solution for evaluating generated text models across all tasks or all properties of text that you may care about. But LLM-guided evaluation can allow for really targeted customization of the criteria that is most important to you and your use case. And prompting alone can be unpredictable and sensitive. So we think that the ability to iterate quickly on feedback, as well as the evaluation criteria that you're using, is crucial to identifying existing weaknesses in your LLM system. This was kind of the inspiration for us developing the Arthur Bench product, which is open source on GitHub. So we encourage you to check it out if you're interested or are developing your own evaluation techniques for LLM systems. We'd love to hear from you.